Hey everybody, want to show you the, let's see, where's our class? The food drive. I actually was kind of surprised. We had a bunch come in the afternoon on Friday. I was beginning to think that I might have to sort of bolster the numbers a little bit, but we came in over, let's about 650 or so. So good job with that. You know, during the like during this season, Thanksgiving and all that, we tried to be grateful for what we have, and you know, we try to do that all the time. But it's kind of hard because sometimes we get sort of wrapped up in our own little problems, and we all have our own little problems. Those are real problems, whether with class or with home or with work or whatever. But it really helps to put things in perspective. Hey, Sadie, help to put things in perspective when we help others because it reminds us that other people have problems too, just like us. And sometimes their problems are even a lot more dire than ours. So really appreciate your work with the food drive. It is a good thing. I know it's not really physics, but I think it's worthwhile to make it part of the class. So as I said, we'll have 10 points that'll be added into the grade. You can take that 10 points and add it to any exam grade. And then we'll have another opportunity for 10 extra credit points at the end of the semester. We'll take an assessment at the end when you take your exam. In addition to that, you'll take another assessment. Don't sweat it. As you prepare for your exam, you'll be prepared for that assessment. You'll be covering the same material for the assessment. And some of the questions will look very familiar to you from your test and from your preparations. Okay? Any news from the weekend? We did Kernel Connect. Did y'all come to Kernel Day when you did, Jesse? Was it useful for you? Did it help you decide? So whether to come to Nichols or not. Oh, you went there this week? I saw you there, yeah. But did any of you go when you were high school seniors? I'm not sure if they had it back then. Did they have it way back when y'all were seniors? Okay. All right. Well, it was a lot of fun to meet all the seniors, to meet people that don't really know what they want to do, just like me and you, right? Do we really know what we want to do? Many of you don't. That's okay. Um, my goal this week is we'll finish up chapter 8 and also at least get a good start on chapter 9 so that if you want to work on the take home, which you'll get this week, you can work on it over the break if you like. But it's not going to be due until the exam, which is a full week and a half after the break. Because after we come back from the break, we have a whole week and then we have Monday. Because I know that y'all have a lot of take homes for the break, right? Do you have a lot of take homes for the break? No, I don't mean for you to work over the break, but if you want to work on it, you may. So you'll have two take-homes. You'll have a derivation, which I'll also send out today or tomorrow, the moments of inertia. It'll be something similar to one we did in class. You can probably find it online and you can work together. And then we'll also have some statics problems, which will be all of Chapter 9. We'll do some examples in Chapter 9. I want to remind you what we did last time. We are into Newton's second law. So you'll see a problem like this. We'll look at some later as well, and you can see them in the old exams, where you have an object that has forces applied to it. Probably what you'll have is an object with a certain moment of inertia, and you'll have forces given in vector notation at a moment arm in vector notation, and you'll have to take the cross product to find the torque. Excuse me. You find the net torque, though, of this object. You find the moment of inertia. And then when you find that, you can figure out what acceleration does that net torque cause in this object. And when you find that acceleration, you can do a whole host of things. You can figure out what is the displacement after a certain amount of time, or what is the speed after a certain amount of time. I also introduced this. You won't find this in old exams, but we'll introduce it again today. We'll look at it. That whenever you have a torque acting over a certain distance theta, then that does work on that object. And we'll see today the work energy theorem. Anytime I do work on an object, it'll increase its energy. We saw that in chapter 5, but we're going to see it again now and in a very similar way, except now we'll be dealing with tau theta instead of FD. That whenever I do work on an object, I apply a torque over a certain angular displacement, then that causes the energy to increase. And we'll see that again, like I said, in just a few minutes. But now let's do clicker question. Y'all go ahead and start on this one. I'll pull up the base. By the way, guys, if you want to help, I'm not requiring it, but if you want to help pack up food for the food drive today, they'll be back in the health and safety building. You know the track that goes on the back of campus? It's that little brick building next to over towards the new wellness center. They'll be there at 10:30, so 10:30 and on throughout the day. So if you want to help them unpack and pack up boxes, let me know. I can send you more information about it if you don't have a busy day already. First thing here, a merry-go-round. You'll want to look on your table where I gave you all the different moments of inertia for different shapes and figure out which of those is a merry-go-round. Which of those shapes is a merry-go-round? And then once you figure that out, you can determine the moments of inertia, determine the torque, the net torque, the angular acceleration, and it looks like we're looking for the speed here after 3 seconds. Which of those shapes are you going to use for a merry-go-round? The cylinder. Make sure you use the right cylinder, the one that goes with the axis down through the middle. Notice that in the cylinder, the length of the cylinder is not important, so a merry-go-round is just a very flat cylinder. It's a disc. First, find the moments of inertia. It's a cylinder. I think that's 1/2 mr squared. Then find the net torque. Here we only have one force being applied, so it's fairly straightforward to find the torque. Then find the angular acceleration. Then find the angular speed. Moment of inertia, torque, acceleration, speed. Yeah, sure. Find your moments of inertia, right? That's 1/2 mr squared. Then you'll need to find your net torque. I only have one force. You need to know the moment arm. It's given in the problem, but determine what is the moment arm. Torque is equal to R times F. Then you need to take Newton's second law, torque equals I alpha, and figure out what the angular acceleration is. And then you should find omega, the speed. All right, we'll do about 10 more seconds. I'll stop at 350. 350. Okay, it's okay, but listen, you're definitely going to have a problem like this on the test, so you need to know how to do these problems. In fact, the problem that you'll have on the test will be more complicated than this. We'll work an example in the next page, I think. But you definitely need to know the process to go through for these. And right now, we're not really shooting that. So first, we want to find the moment of inertia. Then we find the net torque. Then we find alpha. And then in this case, we're looking for omega. what speed has that angular acceleration created. So to find I look up and I realize that, oh, this is a cylinder, and I look up on my table that's on your equation sheet, and I realize that's 1/2 mr squared. 1/2 of the mass is 100 kilograms. The radius is 1 meter. That squared, 1 squared is 1, so that's 50 kilogram meter squared. Then I find the net torque. Now in this case, I have a cylinder. I have a 50 Newton force applied at 1 meter, and so that torque is equal to R cross F, which is RF sine theta. But realize that theta here is 90 degrees, so it's just R times F. So you could have skipped these little steps, and you just realize that this is R times F because sine of 90 is 1, and so that's 1 meter times 50 newtons, or 50 Newton meters. That's the net torque. And then I take Newton's second law, torque equals I alpha. So alpha is torque over I. Here's my torque, here's my I, so this is equal to 1. That's 1 radian per second squared. I know it's radians because everything's in SI units, and radians is the SI unit for angle. And now I'm looking for omega. Could have asked you a couple different things, but I asked you for omega. And omega is equal to omega naught plus alpha t. Let's just go check here. It says it started from rest. As you know, it's usually the case that it starts from rest, but you just want to double check that. So this is equal to 1 radian per second squared times 3 seconds, which is going to be A is the right answer. 3 radians per second is the speed. Could also ask you what is the angular displacement. I could ask you the energy, the momentum. We'll get to those. But in this case, I asked you for omega. Okay? Now, let's say the work energy theorem says that when you do work on an object, you increase its energy. And this also applies for rotating objects. So when I do work on an object, I change its energy. And in this case, we're not changing the potential energy of a rotating object because we don't really have a mechanism to increase the potential energy of a rotating object. But I change its kinetic energy. So anytime I do work on this, I'm changing its kinetic energy. And remember, as we said before, that we saw in chapter 5 that work was equal to force times displacement. In this case, our work is going to equal to tau times theta, our torque times our angular displacement. Let's see, have we given the expression? Yeah, we have. So remember our expression for kinetic energy. Kinetic energy, before it was 1/2 mv squared, and now we have 1/2 I omega squared. If you recall, we went through this whole thing where we made this definition for I back before, where we said, okay, if each point on an object has the same angular speed, then we can relate that to our v, where our v are 1/2 mv squared. And we got this expression 1/2 I omega squared, I was the mr squared. And that's where our definition for moments of inertia came from. But this is our expression for kinetic energy. And so if I do work on an object, then I increase its kinetic energy. So let's say, for example, let's look at this previous problem, and I want to calculate its work. I'm going to calculate it in 2 different ways. I can calculate the work done. Work is equal to tau times theta. All right, so our torque, what was our torque on the previous one? It was 50 Newton meters. 50 Newton meters. And now we also need to know our theta. I'm going to go back up here and I'll figure out what is the theta after 3 seconds. So that's going to be 1/2 alpha t squared. That's 1/2 of alpha, which was 1. That's from right here, times our time, which is 3 seconds squared. And so that's equal to 4.5 radians. So we can figure out the work that's being done on this object. 50 Newton meters times 4.5 radians. Let's see, that's 225 joules. So the work that was done by this torque on that spinning object that moves through this displacement in 3 seconds is 225 joules. Now that will all convert into kinetic energy. All of this goes into kinetic energy. And just to check, sort of make sure that everything is connected and is self-consistent, I can also calculate my kinetic energy. 1/2 I. Our I was 50. Omega is 3. 1/2 of 50 times 3 squared. That's 4.5 times 50, which is also 225 joules. So that's just sort of showing that it's self-consistent, that the work that I do, torque times theta, is 225 joules. I also know that I'm getting up to this speed. We found that in the previous problem. And so the kinetic energy, that rotating body, is 225 joules. All of that work goes into kinetic energy. Okay? Make sure that you know this. You'll see this sort of thing on the test where you have a spinning body and I ask you how much work was required to get it up to this speed, or in this angular displacement, what amount of work did this torque do, kind of like this. It's not going to be no dot product, though we could have dot products involved, but you will not see dot products. It's just torque times theta to find the work that's involved. Very likely. Is that something? Anyway, you're gonna see that. I'm certain of it. Okay? Alright, let's see. I think I have let's just do this example. So how much work is required to stop a thin hoop rotating at 10 radians per second? Uh, and its mass is the radius is 1 meter and its mass is 1 kilogram. So in order to find the work, how much work is required, you have to find the moments of inertia. You look back on your table and look for the hoop. You might remember the hoop. Remember, it was that really simple and it was just, well, I'll let you look it up. Find the moment of inertia of the hoop and then figure out what is the kinetic energy. So I'll let you do that. I'll give you about a minute to get a head start. Try this extra little problem I'm throwing on there. After you find the kinetic energy, if the hoop must stop in 3 revolutions, this hoop is spinning, and you want it to go no more than 3 revolutions, then what tangential force must you apply to that hoop to get it to stop in 3 revolutions? But first, think about the energy. What is the energy of this thin hoop? Remember the hoop. If you haven't found it yet, it's on your table, mr squared. And then this is 1/2 I omega squared. Omega is given right here. You calculate I, which you'll find it to be, what is I? It's 1, right? 1 kilogram, 1 meter squared. So the moment of inertia is equal to 1. And then we find our energy, 1/2 of 1 times omega, which is 10 squared. So that's equal to 50 joules. Now, I want it to stop in 3 revolutions. What tangential force is required? So think about this. What am I going to have to do? First of all, what's my first step to determine this? Anybody know anything stand out on this to you that you'll need to do first? That's right. So you're working with SI units, and so this revolutions will have to go to radians. Listen, if you ever have any doubt, then go to radians. It is the case in some of your kinematics questions that you don't have to convert to radians, but anytime you're dealing with torques, anytime you're dealing with energy, anytime you're dealing with, well, not momentum, but anytime you're dealing with energy, you must convert to radians. If you ever have a doubt, just convert it, okay? Um, and so here you'll definitely need to convert it. 3 revolutions is 6 pi radians, or about 18 point something radians. And then I know that the work required to stop it is equal to the torque times theta. And torque, since this is a tangential force, is going to be Fr times theta. All right, so I say that work, which is 50 joules, is equal to F, which is what I'm looking for, times R, which is 1 meter, that's where the force is applied, times theta, which is 6 pi radians. There are 2 pi radians in a revolution, and so it's 6 pi. So this is 50 divided by 6 pi. It's 2 point something. I don't know what it is. Does anybody know what that is? Be careful with your order of operations. You have to put that in parentheses, the pi. Okay, we'll call it 2.7. So that's in 2.7 radians. Something along those lines is what you'll see on the test as regards to this. That something where it's all connected, you have this force, you have this object that's rotating of a certain shape, which you'll need to look up on your table. Make sure you practice with that table looking at different shapes. Just make sure that you know what's on there. You'll have to find the moment of inertia, find the kinetic energy, and then find the force required to stop that object, the tangential force. And if it was slowed and rest in 5 seconds, how much power was expended? Well, remember our power expression. Our power expression is work or energy over time. The work done was 50 joules. I have 5 seconds. 50 divided by 5 is 10 watts. And so that's the power of this engine or whatever it is that you're using that's required. It's going to be useful when you're dealing with mechanical things. You have these big flywheels. You can determine the amount of energy that's involved in these rotating flywheels. A flywheel is a big disc, right? You have one in your engine. To know what type of motor you're going to need in order to spin that flywheel at a particular rate. So it's a very useful thing to be able to know how to calculate these things because in our mechanical systems we often have rotating bodies. All right, let's try a quick test. This one's similar to the one we did before. Remember, a flywheel is a big disc. These are pretty massive discs. In this case, your first step will be to find the moment of inertia. So find the moment of inertia, and then think about this system. What is it that I have? Well, I have one big flywheel, which is a disc, and then I have another smaller shaft. And that's where the tangential frictional force is working. So I have this big flywheel like this, and then I have this shaft that comes up into the middle of the flywheel, and I have a force that is acting on this shaft. I can't draw it tangentially, but you get the idea that I have this force. This flywheel sits on a shaft and it's spinning, but there's friction between the shaft and whatever it's making contact with. All right. Oh, I'm sorry, you don't need this. This is let's also ask the question, what work is done by this force? I'm going to start filling in some things here. I, for a cylinder, is 1/2 mr squared. That's for my table. 1/2 of, is that 33,000? Times 1.4 meters squared. Oh, that's my calculator. Shoot. I get 32,000. Is that right? No. Or 3.2 times 10 to the fourth. That's in kilogram meters squared. What's going to be my next step? After I find the moment of inertia, what will be my next step on this? All right, just slow down. Not everybody at once. Like you can just raise your hand. What is my next step? Come on. After I find my moment of inertia, I want to get to the angular displacement. I want to get to the angular acceleration. What do I need to know next? Okay, I need to find alpha, but before I can find alpha, I have to find the torque. Right. So next step is to find the torque, because I'm looking for the angular acceleration. That'll get me to where I want to go. But next, I have to find the torque. And there's only one force here that's causing a torque. That's this 28 kilonewtons. 28 times 10 to the third newtons. And now I need to figure out, well, what is the moment arm? I have two distances sort of floating around. I have the 1.4 meters, and then I have the 21 centimeters. Which of those, the first or the second, is the moment arm for this force? What now? What do y'all think? I have this big flywheel right here, and then I have this shaft coming down that's 21 centimeters in diameter, and the force is applied where? To the big flywheel or to the shaft? The shaft, right. So be careful. You want to make sure that you pick out the right moment arm, because in this case the moment arm is what? It's the shaft. So it's 21 centimeters is the diameter. So half of 21 is what? 10.5. So it's 0.105 meters. That's half of 21 centimeters. And that gets me 28,000 times 0.105. I get 2,900. That's in Newton meters. And then I want to know alpha. And so to find alpha, I say alpha is torque over I. It's 32,000, or excuse me, 2,900 over 32,000. And I get 0.091. That is my angular acceleration in radians per second squared. And then the next question is T. How long does it take after I found alpha, you're going to have those steps on every problem. So when you encounter a problem like this, know that you'll have to go through each of these steps, I, torque, and alpha. And now I go to the problem and it becomes really just a kinematics problem. Is that 0.105? Oh, so the, the diameter of my moment arm is 21 centimeters. 21 centimeters, that's equal to 0.21 meters, and then the radius is 0.21 divided by 2, which is 0.105 meters. Okay? But to read these carefully, make sure you pick out if it's the diameter or the radius. Though if you didn't do that in this case, I would count on maybe a point. Okay? Um, so that's my alpha. Now I'm looking for the time. Reading this question, this is what I'm looking for. So T is what I want to know. I want to know how long it'll take to coast to a stop from its normal rotation rate of 420 revolutions per minute. So when it says to a stop, what is this referring to? Is it referring to alpha, omega, omega naught, theta? What is this word referring to? Okay, omega or omega naught? Omega, right. It is omega because it's starting at some speed and then it's coming to a stop. So if it was to say it started from rest, then that would be omega naught. But that's not the case here. I know that omega, which is my final speed, is equal to 0 radians per second. And my initial speed is 420 revolutions per minute. So omega naught is 420 revolutions per minute. You'll need to convert this. 1 minute, 60 seconds, 1 revolution is 2 pi radians. I get 14 pi, which is 44. So this is 44 radians per second. Okay, so now I know alpha, omega, and omega naught. I want to find t. So let's say omega equals omega naught plus alpha t. And so t is omega minus omega naught over alpha, which is going to be negative 44 divided by 0.091. And I get 480, negative 480 seconds. So it takes almost 500 seconds, or excuse me, oh, so what mistake have I made here? I can't have a negative time, can I? So what's my problem? Um, Either my omega naught needs to be negative or my alpha needs to be negative. I'm going to make my alpha negative. The reason I'm making it negative is so it's in the opposite direction as the omega. We haven't really been given any directional information, so we don't know is it going clockwise or counterclockwise, but I do know that the angular acceleration is opposite the direction of the angular velocity. Now, how do I know that? Why is the angular acceleration opposite the direction of the angular velocity? Because it's slowing down. And if it's slowing down, just like we had in chapter 2, the velocity is opposite the acceleration. So this thing is slowing down, so I get a positive time. Okay, so that's part A. Part B is theta. We're in the home stretch now. I say theta equals omega naught t plus 1/2 alpha t squared. Being careful here because omega naught is not 0. Omega naught is 44 radians per second times 480 plus 1/2 of alpha, which is 0.091 negative times 480 squared and I get 11,000 radians. So what y'all got? 11,000, you know, radians. You might have rounded off a little bit differently along the way. And so that's my theta. So this is part B, this is part A. And now to find part C, remember for part C, we want to know what is the work done. Our work is equal to torque times theta. Couple ways you could do this, by the way. Actually, you could figure out what is omega, or we know omega, excuse me. We could say that we could take this value and say whatever kinetic energy the thing had in the beginning, that amount of work had to be done to take all that kinetic energy away. And so you could say 1/2 I omega squared. And you have everything you need to know how to do that. Or you could say the work is torque times theta. That's going to be, the torque was 2,900 times 11,000. 290 or 2,900? Yeah, 2,900 Newton meters times 11,000 radians. And that gives me the work that that force did, or that torque. 3.2 times 10 to the 7th. That's a lot of energy. So these big flywheels, as I said in the problem, they'll use these flywheels to store energy. And then they have these huge rotating flywheels, then they can use that energy later for whatever it is they want to do, to drive a turbine or whatever they want to do. Okay? So that's how you find the work that's being done by this force. Or as I said, you could also, to be okay too, you could say that the kinetic energy is 1/2 I omega squared. I we found, omega we know. I is 32,000. Omega is 44 radians per second. And you should get something similar, around 32 million joules. You might get slightly different because of rounding, but okay. That's a good example of a test question. The one thing that you might see differently as you go back and look at old tests is that sometimes I'll give the force in vector notation and the moment arm in vector notation. Don't be thrown off by that. All you got to do is do the cross product. We've done cross products, and you're going to see a cross product, but you might see it in a question like this, or you might just see it all by itself, where I just, hey, here's a force, here's a moment arm. What is the torque being done by this force? But you'll definitely see a cross product. Okay? I think we're good on cross products. If you're not, remember you'll see one. You'll also see a problem like this for Newton's second law. In fact, on this next test, you're really only going to have 2 chapters on it. You'll have this chapter, which has a lot of material, and then also you'll have the chapter on optics, which you're going to like. It's a fun chapter. Okay? All right. There's one more topic in this chapter, which is on angular momentum. You'll also see a problem like that. Now remember the expression we have for linear momentum? We call it P, and it's equal to the mass times the velocity. P is equal to the mass times the velocity. Hey, if I told you this, what's the worst thing about living on O Street? You have to walk a whole block to P. Sorry, the momentum just reminded me of that. That's a good joke, right? It's like a middle school joke. I'm sure you'll be telling your friends all day today. All right, but anyway, this is our linear expression. Now we also want to have an expression for angular momentum, because an object that's spinning also has momentum. But remember, in our sort of scheme that we've been talking about, our mass has now become what? Whenever we have mass, which is a measure of inertia, we now have what instead? How do we measure inertia in a rotational system? Not m, but I. Thank you. Our moment of inertia. So anywhere we had m before, we now have I. And our v, which is a measure of velocity, we're now going to have that what? that little curly omega looking thing. So our angular momentum is the product of the moment of inertia and the angular velocity. And this L, we'll call it L, is equal to I times omega. Actually, really what it is, we're not going to use this, but it's really L is equal to I cross omega. These are vector. Wait, no, 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 no. They're not vector point. Never mind. Not sure if that's true. Never mind. Don't write that down. I'm not sure that's true. But L is equal to I times omega. These are vector quantities, not I, but omega is a vector quantity. And so we'll need to treat them like vectors, but kind of in the same way as we did with the linear momentum, where we had, one was in one direction and one was in the other direction. Now we did have 2D vectors when we did linear momentum, but we're not going to have the equivalent here. We'll have momentum in one direction or momentum in the other direction. And so the vector business doesn't really uh, cause too many kinks. The unit for angular momentum is the kilogram meter squared per second, that's the unit of I, which is kilogram meter squared. The unit of omega is 1/2. So it gives us this unit for angular momentum. Again, as you know, on the multiple choice, you can see questions just what is the basic SI unit? You probably will. And we have a lot of different quantities for torques and rotational energy and angular momentum and all the various quantities that we've had. So make sure that you're able to do that. Don't memorize the units, just be able to look at the equation and then figure out what the units are through the equation. Okay, so as with linear momentum, remember we said that Pi was equal to Pf? As with that, angular momentum is also conserved. That is that Li is equal to Lf. Usually what we're going to see is that we'll see one object that's spinning, and then we'll change its moment of inertia in some way by engaging it with some other object. Sometimes we'll see two spinning objects, and then we'll engage them together, and then they will spin at new speeds. But usually we'll have one object, and we'll change its moment of inertia in some way. Um, well, let's just do a sample problem, and then we'll do this clicker question next. So let's say that I have a bar. I have a bar that's rotating about this axis. It has a length B, I think B is what we called it. B is equal to, say, 2 meters, and the mass is 3 kilograms. All right, so I have this bar, and let's say that it's rotating at 2 revolutions per second. It's rotating about this axis. Say there's a shaft right there about which it's rotating. And then I also have a disk, a flat disk, that will now be connected on the same axis. And it has a radius equal to 1 meter and a mass equal to 2 kilograms. Initially, it is not spinning at all. So initially, these two things are separated. They're spinning on two independent axles, but then you connect the axles together with gears or whatever, however you connect these two axles together. And now this spinning bar, which was spinning at 2 revolutions per second, will connect with the stationary disk, not spinning at all, and they're going to both spin now at a new rate. Are they going to spin faster or slower than 2 revolutions per second? They're going to spin slower, right? Because some of the rotational energy that this thing has, or actually some of its angular momentum, will be transferred also into the disk. And that'll cause both of them to travel slower. Now what you need to do in this is you need to figure out what is Li, and Li will equal to I of the bar times omega of the bar, and then figure out what is Lf. And Lf will equal to I of the bar plus I of the disk, because they're now connected, times the omega of the system. And what we're looking for is this new speed. What is the new speed? Because of the conservation of angular momentum, Li will equal to Lf. And so we'll set those two equal and solve for our new omega. We'll do this over here. What is I of the bar? So you want to use your table, go over to your table and figure out, try to determine what is the expression for the moment of inertia for that bar. Okay, so I for a bar is 1/12 mv squared. And so that's going to be m is 3, 2 squared is 4, 3 times 4 is what? Is 12. So this is going to be 1 kilogram meter squared. What I did there is I took the mass of the bar, which is 3 kilograms. The length of the bar is 2 meters. Square it. 1/12 of 3 times 4 is equal to 1. And then you need to do the same for the disk. For a cylinder, the moment of inertia, you'll probably memorize this now, but it's 1/2 mr squared. So that's 1/2 of the mass, which is 2 kilograms, times the radius, which is 1 meter squared. And so that's also equal to 1 kilogram meter squared. So what is our new speed? What is our new speed? Well, by how much have I increased the angular, or the moment of inertia? I've increased it by what factor? I went from 1 kilogram meter squared to what's my new moment of inertia? It's 2, right, because I had 1 before, and now I have 1 plus 1. So I've increased my moment of inertia by a factor of 2. What's going to happen to my angular speed then? Is it going to increase or decrease? It's going to decrease. And by what factor is it going to decrease? What factor is it going to decrease? 2, all right? Because right here I have this Li equals Lf. That is I initial, omega initial, equals I final, omega final. If I goes up by a factor of 2, then omega goes down by a factor of 2. But we can do that by setting these two quantities equal to one another. And I'll do that down here. I of the bar was 1 kilogram meter squared, and it was moving at 2 revolutions per second. And now the I of the bar plus the I of the cylinder, 1 plus 1, and omega final. So this is 2 equals 2 times omega. So omega, where it was 2 revolutions per second, now it's 1 revolution per second. All right, just a little note of caution. Notice I did not convert my units to radians, because if you follow your dimensional analysis as you go through here, you'll see that if I have revolutions per second over here, I can also have revolutions per second over here, that the revolutions will cancel out. And so I can keep it in revolutions per second when I'm dealing with angular momentum. Just if that bugs you or that feel like that's just confusing to you, then you could convert that to radians per second, and that would be just fine. And I wouldn't count off anything for the answer. It would still be just as correct as this answer. If ever you doubt, just convert to radians, because that is your SI unit. Okay? Let's try this clicker question, then we'll wrap it up. Now in this case, I have a kid, or I have a merry-go-round that have a certain moment of inertia. A merry-go-round, remember, is just a flat cylinder. It's a disk. So it has a moment of inertia. It's spinning at 2 revolutions per second. And then a kid comes and jumps onto the outer edge of this merry-go-round. So this merry-go-round It's spinning at 2 revolutions per second. But then I have a kid that comes and jumps onto the outer edge. How am I going to treat that kid? Looking at your table or thinking about your table, or not thinking about your table, maybe you don't need the table at all. How am I going to treat that kid? How will I determine the moment of inertia that that kid contributes to the system? Remember, we had two different things when we deal with moments of inertia. We have that table, but then we also had this deal where we just dealt with particles. Remember, we did an example early on where we had the three masses, and I said mr squared for the first mass, plus mr squared for the second mass, plus mr squared for the third mass. And I added those three up. What would be the case here? Would I use the table, or would I treat the kid just as a particle of mass? You treat them as a particle of mass, okay? So when you're determining your final moments of inertia, you're going to treat this as a cylinder, but you're going to treat the little boy as just a particle of mass. We're assuming that he's a lot smaller than the merry-go-round, which is a pretty good assumption. 2/3 of you have it right now. That's awesome. All right, we're almost out of time, so I'm going to give y'all about 15 or 20 more seconds. I'm going to stop at 3 minutes, just 5 more seconds. Just guess if you're not sure. Okay, let's see. D is the right answer here. B is sort of the next best wrong answer. My moment of inertia of the disk is 1 kg/meter squared. The moment of inertia of the kid is also 1 kg/meter squared. And we'll come back to this after. I'll show you this when we come back, so we'll have more time to spend on it. Okay? So y'all have a great day. Again, if y'all want to come help out at the Health and Safety building, you can come at 10:30. Just let me know. I'll give you more information. And good job with the food drive. And I will see y'all on Wednesday.